Picture the universe as a book, then realize the first chapter is missing. We can read the cosmos back to a time when everything was hotter than stars, denser than any matter we've ever touched. But the closer we get to the first line, the ink starts to blur, not because there was nothing, but because our laws of physics stop agreeing with each other. And that raises a haunting possibility. The Big Bang may not be the start of everything, only the start of what can be measured. Stay with me, because by the end, you'll have a crystal clear answer to the question, did anything exist before the Big Bang? And you'll know exactly where certainty ends and imagination begins. Before we begin, thank you for being here. If you feel connected to this space, a simple like or subscribe really helps this video reach more curious minds like you. Now, let everything soften, and together we drift into space. Before we touch any evidence, before we reach for telescopes or equations, we have to do something harder. We have to slow down long enough to notice how strange our own question really is. Did anything exist before the Big Bang? It sounds simple, almost casual, but the moment we say it out loud, we're already smuggling in an assumption that before is a place we can walk to, that time stretches behind the universe like a dark hallway, that the cosmos is a story with earlier pages we can always flip back to. Except the universe does not always honor the grammar of our instincts. And if we're going to be honest, if we're going to be scientific, then the first task is not to answer the question. The first task is to define what we mean by the Big Bang, the way cosmologists mean it. Because the Big Bang is not a fireball that went off somewhere. It is the moment the universe first becomes readable. And everything we want to know depends on where that record begins. In modern cosmology, the Big Bang is not a single event we can point to in space. It is a model, grounded in Einstein's general relativity, describing a universe that has been expanding from a much hotter, denser early state into the vast, cooler cosmos we inhabit now. That word expanding matters, not expanding like smoke filling a room, not expanding like debris flying outward from a bomb, expanding in a deeper way, space itself stretching, carrying galaxies apart, not because they are running through space, but because the space between them is growing. This is why the Big Bang is often described as the beginning, but not in the way the human mind wants. It is not a spark inside a pre-existing darkness. It is the earliest chapter of a universe whose pages are written in expansion, cooling, and light, and the name Big Bang is almost a trap. Even NASA has pointed out how misleading the explosion imagery can be, because explosions have centers. The Big Bang does not. So when we say the Big Bang, what we are really saying is the universe used to be hotter and denser than anything we can naturally imagine, and it has been unfolding ever since. But then the story tightens, because hot and dense is not poetry, it is physics. When we rewind cosmic history, when we follow the mathematics backward, the universe does not just get smaller, it gets more intense, hotter, denser, more energetic, so energetic that atoms could not survive. Not because they were broken, but because the universe was a kind of searing ocean of particles and light, so packed, so violent, that stable atoms were impossible. This is not guesswork in the casual sense. NASA describes the early universe as a tremendously hot, dense state, and places the broad timeline at about 13.8 billion years ago. And here's where our imagination tries to do something dangerous. It tries to picture a tiny ball sitting in empty space. But that picture breaks the moment we look at what space even means in relativity. Let's do one clean, uncomfortable thought. Imagine a loaf of bread rising in an oven, not a loaf sitting inside the kitchen expanding into the air. The loaf itself is what's changing, every part of it swelling, every point moving away from every other point, not because there's a center pushing outward, but because the dough everywhere is stretching. That's closer to what cosmologists mean, except the universe is not dough, and there is no oven. There is no outside space the universe is expanding into. The Big Bang is better understood as the expansion of space itself, happening everywhere at once. NASA astrophysicist John Mather put it bluntly: the Big Bang did not occur at a single point in space like an explosion. What we call the Big Bang is tied to the idea of space appearing and expanding everywhere. So when we ask, where did it happen? The honest answer is, it happened here, and there, and in every direction. Not because it was scattered, because the universe at that time was the whole stage. There was no backstage, and this is why before starts to feel unstable. But we're not there yet. First, we need to ask a more disciplined question. What can cosmology actually observe, and what must it infer? Cosmology is powerful, but it is not magic. It does not see the beginning like an eyewitness. It reconstructs the past the way we reconstruct a crime scene, using traces that survived: light, motion, patterns, temperature, and those traces have limits. Even with the James Webb Space Telescope, built to see the earliest galaxies, we are still watching light that has traveled for billions of years before it reaches our eyes. We can observe the universe expanding through the way galaxies appear to recede. We can observe fossil light that fills all of space, but we cannot simply look past a certain wall, because the early universe was not transparent. It was opaque. It was a glowing fog of charged particles that scattered light in every direction, like a headlight beam swallowed by thick storm clouds. And until that fog cleared, light could not travel freely, meaning the universe could not leave us an image. It could not leave us a picture. Only later did it become quiet enough for light to slip through, which brings us to the first hard edge of our cosmic record. The furthest back we can explore using light is the cosmic microwave background, the CMB. This is not a metaphor. It is real radiation, still present today, spread across the entire sky. ESA explains it clearly. The CMB formed about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form, allowing light to finally travel long distances without constantly bouncing off free particles. Harvard and Smithsonian describe that early era as a hot soup where photons couldn't get far, until expansion cooled the cosmos and made it transparent. So the CMB is the first page we can read directly, and notice what that means. When we say we can see the early universe, we're not seeing time near zero. We're seeing a universe already hundreds of thousands of years old. It's like trying to understand a person's birth by looking at a photograph taken when they're already a toddler. Still young, still revealing, still astonishing, but not the first breath. And beyond that first readable light, we enter a realm where observation becomes reconstruction, where we don't have a photograph. We have fingerprints, we have shadows, we have evidence that survives without giving us a direct image. NASA describes the CMB as the heat signature left by the Big Bang, visible from that early time, around 380,000 years after it happened. But everything earlier than that is harder. Not necessarily unknowable, but harder, because the universe in its earliest moments hid itself behind its own density. And now, here is the moment where our question changes shape, because before the Big Bang sounds like a door we might force open, but what we actually have is a boundary, a horizon of evidence, a limit drawn not by human curiosity, but by the physics of a universe that once could not let light travel. And this is where we need one sharp, personal anchor. You can turn on a flashlight in a clear room and see the beam cut through the air, but if you fill that same room with thick smoke, the beam doesn't reach the far wall. It scatters and dies close to your hand. The early universe was that smoke, except it was made of plasma and radiation, and it filled everything. So when we ask what happened earlier, we are asking what happened in a room where the light could not yet cross the room. And that is not a philosophical limitation, that is a physical one. So the Big Bang, as science uses the term, is not a bang. It is the beginning of a measurable story. Expansion from a hot, dense state, described by tested physics, anchored by observable traces. And the earliest direct light we can read, the oldest image we can ever take, is the CMB, released when the universe was about 380,000 years old. Everything earlier is not automatically fantasy, but it is not directly visible. It must be inferred carefully, through what that later light remembers, through what matter retains, through patterns that survived the furnace, which leaves us with a quieter, sharper version of our original question. Not, did anything exist before the Big Bang, but something more disciplined, something that actually decides whether we're doing science or just daydreaming. What do we have that proves the universe really did begin in that hot, dense state, rather than merely assuming it? There's a quiet kind of evidence in cosmology, not a single photograph, not one dramatic snapshot, more like a fingerprint on glass that refuses to wipe away. Because when we look out at the deep sky, we're not just seeing far, we're seeing earlier. And the unsettling part is this: the farther we look, the more the universe behaves like it's running away from itself, as if the past is still expanding in our hands. Imagine you're holding a long, thin rubber band between your fingers. You draw a few dark stripes across it with a marker, tight, neat, close together. Now you slowly pull your hands apart. Those stripes don't vanish. They don't jump to a different place. They simply spread. The pattern survives, but it's stretched. That is the simplest, honest picture we have of what happens to light in an expanding universe. In the 1920s, astronomers were staring at faint nebulae and wondering what they really were. Edwin Hubble helped settle that argument. These were other galaxies, far beyond the Milky Way. But then he and others noticed something worse. Their light wasn't just dim, it was shifted. When astronomers split galaxy light into its rainbow using spectroscopy, they saw familiar spectral fingerprints displaced toward the red end. Not because the galaxies were red objects, but because the waves of light had been stretched during their journey across expanding space. And then the pattern sharpened into a law-like threat. The farther the galaxy, the stronger the redshift. Distance and recession were linked. So reliably it became known as Hubble's law. This is where the universe stops feeling like a place and starts feeling like an event still unfolding. Because an expanding universe isn't just a moving collection of galaxies. It's a cosmos whose very geometry makes ancient light arrive altered, carrying the stretch of space inside it. When we put numbers on this, the human mind flinches. NASA's Hubble team describes the expansion rate in a way that sounds almost casual until we translate it. For every additional 3.3 million light-years away, a galaxy is, it appears to be moving about 74 kilometers per second faster, about 46 miles per second, because space itself is expanding. That's about 266,000 kilometers per hour, roughly 165,000 miles per hour. At that speed, you could circle Earth roughly 6 to 7 times per hour. And yet, that speed is attached to distance. It compounds with scale. So the uncomfortable realization is not, things are moving fast. It's this. The universe has been stretching for billions of years, and the stretch is still written into the light we receive right now. But then the story gets stranger. Because galaxies are only the first clue. They're messy, they evolve, they collide, they light up and fade. So cosmologists asked for something colder, cleaner, older, something closer to the beginning. There is a faint radiation filling the entire universe, not from stars, not from galaxies, not from any single direction. It's everywhere, like a background hum behind reality, the cosmic microwave background. The CMB, ESA describes it plainly. It's leftover radiation from the Big Bang, and it's the farthest back in time we can explore using light, released when the early universe became transparent. For roughly the first 380,000 years, the universe was like a thick fog of charged particles, photons constantly scattering off free electrons. Light couldn't travel far. Space was bright, but opaque. Then expansion did what expansion always does. It cooled the cosmos. Electrons joined with protons to form hydrogen. The fog cleared, and suddenly light was released, free to travel across the widening universe for the next nearly 14 billion years. That light is still here, but now it's been stretched into microwaves, cooled to about 2.7 Kelvin, around minus 270 degrees Celsius, just above absolute zero. NASA's WMAP mission measured that afterglow as a nearly uniform temperature with tiny variations. Differences so small they read like whispers, but they carry the seed pattern that later grew into galaxies. This is not philosophy. This is measurement, a sky-filling fossil, a baby picture taken when the universe was still too young for stars, too young for planets, too young for anything we'd call familiar, and it leaves us with a brutal implication. If the universe was once hot enough to glow everywhere, then it had to be denser, younger, and more compressed than it is now. But even that isn't the whole case, because light alone can be deceiving, so cosmologists went hunting for an entirely different kind of evidence, not in radiation, but in matter. Hydrogen is everywhere, helium is everywhere, and that alone is already a clue. NASA's own overview of cosmic history describes the early, minutes as a time when the first nuclei formed, hydrogen and helium, with traces of other light elements, before the universe expanded and cooled too much for that process to continue. But the deeper point is this. We can calculate what a hot, dense, early universe should have produced, and then we can measure what the oldest environments actually contain. The particle data group, one of the standard references physicists use to summarize what's known, describes how nearly all neutrons in the early universe end up locked into helium-4, giving a primordial helium mass fraction of about 1/4. That's an eerie match to what we observe at cosmic scales, and it goes further. The same reference describes leftover abundances of deuterium, hydrogen with an extra neutron, at only a few parts in 100,000 compared to ordinary hydrogen, and explains how modern observations of distant, low metallicity systems can trace that primordial value. Britannica summarizes the same backbone of evidence in plain language. The theory predicts definite amounts of hydrogen, helium, and lithium, and their abundances agree with what is observed today, alongside the existence of the cosmic microwave background at about 3 degrees above absolute zero. So we have three pillars that don't rely on a single instrument, or a single team, or a single era of research. Galaxies show expansion through redshift. The sky carries an ancient afterglow, the CMB. The universe is chemically stamped with light elements that make sense only in a hot beginning. That's why cosmologists say the Big Bang model is supported, not assumed. It isn't a story we tell because we want an origin. It's a model we keep because the universe keeps confessing, in independent languages, that it once lived in a hotter, denser state. And still, scientists don't relax. They rarely do. Because even inside the evidence there are tensions, places where the universe refuses to be perfectly neat. NASA explains that different methods for measuring the expansion rate, the Hubble constant, do not perfectly agree. Some measurements land around the low 70s kilometers per second per megaparsec, while values derived from the CMB land closer to the high 60s. That disagreement doesn't erase the expansion, it sharpens the stakes. It's a reminder that we are not reading a simple children's book. We are reconstructing a crime scene billions of years old, with only photons and fossils to testify. And the more precisely we measure, the more we notice the universe has edges we don't yet understand. And if you let yourself feel it for a second, If you imagine you standing in a perfectly dark field, hearing a sound that seems to come from everywhere at once, that's the CMB, a thin, cold echo filling all directions, telling us the universe was once so hot that space itself glowed. Not in one region, not near a center, everywhere, at once. So when we say the universe had a beginning, we don't mean a mythic moment with a dramatic soundtrack. We mean this: the evidence forces us toward a past state where the universe was smaller, hotter, and denser than anything we see today, so extreme that light and matter behaved like a single trapped fog until expansion made the cosmos transparent. We didn't decide to believe this because it's satisfying. We backed into it because multiple independent measurements cornered us, and that creates the next, almost irresistible move, because once we accept expansion as real, and the afterglow as real, and the chemical fossils as real, there's only one thing a scientific mind wants to do. It wants to reverse the film, to take the universe we see and mathematically run it backward, toward higher temperature, higher density, and earlier time. But then the story cracks open, because rewinding the universe is not the same as understanding the beginning. And the moment we start turning that cosmic clock in reverse, we discover exactly where certainty starts to fracture. There is a temptation that arrives the moment we accept what the sky has been telling us. If space is expanding, if light is stretched by that expansion, if the afterglow still fills the cosmos, then our hands start reaching for the same forbidden control every human mind reaches for, sooner or later: rewind, to take the universe we see now, cold, diluted, structured, and run it backward into its earlier shape. And this is where cosmology becomes unsettlingly precise, because rewinding isn't a metaphor for them. They don't do it with imagination, they do it with equations. Equations born from Einstein's general relativity, refined by Georges Lemaitre, and tested against the sky until the sky either agrees or refuses. And when those equations are pushed backward in time, the story tightens like a noose. Space contracts, distances collapse, and the universe does something almost violent. It heats up. In the simplest language cosmologists can use, the universe has a size that changes with time, what they often call a scale factor. As that scale factor increases, space stretches. As it decreases, space compresses. And the equations of modern cosmology connect that change in size to what the universe contains: radiation, matter, and whatever is driving cosmic acceleration today. So when we run the equations backward, we're not guessing what the early universe was like. We're following a chain of consequences. If the universe is expanding now, it was smaller before. If it was smaller before, energy was packed more tightly. If energy was packed more tightly, temperatures were higher. If temperatures were higher, the rules of chemistry and even the structure of matter were not what they are today. And this is where the story starts to feel like it's accelerating toward a cliff. Because unlike human history, cosmic history doesn't become vague as we go backward. In some ways, it becomes simpler, hotter, denser, more uniform. Almost like the universe is trying to erase its own details the closer we get to the start. Picture a pot of soup on a stove. When it's cold, you can see everything in it: chunks, herbs, separate ingredients. But as it boils harder and harder, the details vanish into turbulence. Everything becomes motion. Heat doesn't just change the soup, heat destroys distinction. That's the early universe. Rewinding doesn't take us to a tidy origin scene. It takes us into a boiling state where stable structures can't survive. Not because they were broken by an explosion, but because the entire cosmos was too hot to allow them to exist in the first place. This is one of the cleanest truths in all of cosmology. As the universe expands, it cools, which means as we rewind, it heats. The cosmic microwave background, the CMB, still measures this cooling today, sitting at about 2.7 Kelvin, around minus 270 degrees Celsius, just above absolute zero. But rewind far enough and that calm, cold background becomes something else entirely. A bright plasma fog, hot enough that electrons and nuclei couldn't stay together, scattering light over and over until the universe finally cooled enough to become transparent. And earlier than that, chemistry itself collapses. Atoms can't exist. Nuclei can't survive for long. Matter becomes a seething mix of particles and radiation, all governed by conditions far beyond our daily intuition. Cosmologists call parts of this history the thermal history of the universe, because the story is written in temperature. And here's the disturbing part. A lot of that early physics is not purely theoretical. Some of it is connected to experiments we can do on Earth. Particle physics labs can recreate pieces of early universe conditions, not by building a tiny universe, but by reaching extreme energies for tiny moments, probing how matter behaves when it's pushed toward those ancient states. We're not watching the beginning directly, but we're testing the rules that would have governed it. And still, the deeper we rewind, the less comfortable that confidence becomes. There's a reason cosmologists sound calm when they talk. It's not because they feel safe, it's because they've learned where certainty ends. The equations of general relativity are incredibly successful at describing the expanding universe, how geometry evolves, how matter and radiation shape the motion of space. But those same equations, when pushed toward the earliest moments, point toward conditions so extreme that our current physics stops being complete, not because the universe becomes mystical, but because our models become incomplete. There is a difference, and cosmologists treat that difference with almost brutal discipline. Because extrapolation is not proof, it's a controlled extension of what we know into a region we cannot fully test. And it has a boundary, a line where the known laws, especially gravity and quantum physics, are both needed at once, yet refuse to merge cleanly into one consistent description. The farther we rewind, the more we approach that line, and the universe doesn't gently blur there. It sharpens into a contradiction. Math is powerful, but math is not a passport. Equations don't guarantee reality beyond the conditions where they've been tested. They can guide us backward with astonishing reliability through much of cosmic history, because the early universe was, paradoxically, simpler than the universe now. Fewer structures, more uniform conditions, cleaner physical regimes. But rewind far enough, and we demand something impossible from our current understanding. We ask for a theory that can handle the geometry of space-time and the quantum behavior of nature at the same time, and we do not yet have that full theory, so the math keeps going. But the meaning of the math becomes questionable. It's like having a map that confidently draws roads into a region no one has ever surveyed. The lines may look clean, but that does not mean they correspond to something you can walk on. This is why cosmologists speak carefully. They do not claim to know what happens arbitrarily close to the beginning. They can describe a great deal of early cosmic history with strong confidence because it connects to observation and tested physics. But they also acknowledge a frontier where our best descriptions stop being complete. And that frontier is not just academic, it changes what we are allowed to ask. And if you want to feel the boundary, not just understand it, picture you standing at the shoreline at night. You can see the waves close to your feet. You can hear the ocean farther out. You can even sense the scale of it. But beyond a certain distance, the darkness wins. Not because the ocean stops existing, but because your eyes stop receiving information. Cosmology has that same edge. We can see far, we can infer farther. But eventually the universe becomes so extreme that our current eyes, our current physics, no longer form a complete picture, and the honest mind does not pretend otherwise. So rewinding the universe does something profound. It doesn't just take us closer to an origin, it forces a choice. Do we keep speaking confidently, even when our tools stop being complete? Or do we do what science is supposed to do? Stop at the edge of evidence and admit, with discipline, that a boundary has been reached. The Big Bang model is supported because it explains what we observe: expansion, the CMB, the thermal history implied by the sky and matter itself. But when we push beyond the earliest eras where our physics is securely tested, we don't find a neat answer waiting. We find a crack, a place where the universe demands a deeper theory than we currently possess. And that is where the story becomes almost unbearable in its simplicity. We can rewind the universe back toward a beginning, but there is a moment where the equations stop feeling like a window and start feeling like a warning, because somewhere ahead, in that compressed, violent, primordial state, the physics we rely on begins to break. If we keep running the universe backward, everything tightens. Space contracts, light blue shifts, temperatures climb, density rises towards something almost monstrous. And for a while, the math behaves like a faithful guide. It leads us through a young universe where radiation dominates, where matter is a hot fog, where atoms can't hold together, where the cosmos is still learning how to become transparent. But then, something changes, not in the sky, in us. Because the closer we push toward the beginning, the more our best physics starts to sound unsure. Not because the universe becomes mystical, because we reach a regime where our tools stop being complete. And that regime has a name, a quiet name for a brutal boundary: the Planck time. The Planck time is unimaginably small, about 10 to the minus 43 seconds after the Big Bang. That number is so extreme it barely fits inside human language. So let's translate it into something we can feel. A single second is already a long moment for physics. In 1 second, light can circle Earth more than 7 times. Now imagine cutting that second into 1 trillion pieces, then cutting one of those pieces into 1 trillion again, then again, and again, and you still would not be close. That's how far down this timescale lives, beneath intuition, beneath ordinary cause and effect, beneath the everyday meaning of moment. But the Planck time is not famous because it's small. It's famous because it is where general relativity stops being trustworthy on its own. Caltech's NED Cosmology Glossary puts it plainly. We have strong reasons to suspect that at about the Planck time, calculations based only on classical general relativity should be distrusted because quantum gravitational effects should be large. So the Planck time is not the first instant we can confidently describe. It is the opposite. It is the line where our confidence breaks. Imagine you're trying to read a book through glass. At first, the words are sharp. You can trace each sentence, you can follow the story. But the closer you press your face toward the glass, the more you notice something disturbing. The surface is scratched, not enough to ruin the page from far away, but enough to distort the letters up close. At a distance, the story makes sense. Up close, the medium itself becomes the problem. That's what happens when we push cosmology toward the Planck time. Our glass, our physics, develops scratches. Not because the universe stops obeying rules, but because we don't yet have the full rulebook for that regime. Here's the uncomfortable truth. We live with 2 towering achievements of modern science. General relativity describes gravity as the curvature of space and time, tested from the bending of starlight to the dynamics of galaxies. Quantum physics describes the subatomic world, tested to absurd precision in laboratories. Both are real, both work, both are verified. But at the Planck time, the universe demands that we use both at once, because the densities and energies implied by rewinding cosmic expansion are so extreme that gravity is no longer a gentle background force. It becomes dominant, and at the same time, the scales involved are so small that quantum effects can't be ignored. That means we need a theory of quantum gravity, a description of gravity that behaves consistently in the quantum regime. And as Caltech's NED notes, this is exactly why the Planck time marks the limit of validity for applying classical general relativity within these early universe models. Britannica reinforces the same core idea through the language of the Planck era, describing the Planck time as the timescale associated with when the universe would approach Planck scale conditions. So this is not a philosophical issue, it's a technical one. Our current theories were built for different regimes. Relativity was built for the smooth geometry of the large-scale universe. Quantum physics was built for the grainy, probabilistic behavior of the very small. At the Planck time, the universe is both, and this creates a deeper problem, because when our theories conflict, it's not the universe that becomes unreliable, it's our description. People sometimes hear this and imagine a dramatic moment where physics ends. That's not what it looks like in real cosmology. It looks quieter, colder, more disciplined. We can push the equations backward, and they can continue producing numbers. But those numbers begin to drift outside the domain, where the underlying assumptions are justified, and that means the equations stop being answers. They become extrapolations. A controlled guess based on patterns that worked before. An extrapolation has a limit. Caltech's NED phrasing is careful. We have convincing arguments for when quantum gravitational effects should be large, and that's the region where we should distrust calculations that ignore them. That is what it means when equations stop giving answers. Not that the universe becomes nothing, not that reality becomes nonsense, but that we reach a frontier where our current framework can't be honestly extended without admitting what's missing. And this distinction matters because it changes how we interpret the most dangerous word in cosmology, singularity. A singularity is not a place where the universe began as a point. In practice, it often signals something else, a theory being pushed beyond its ability to describe reality, a map insisting there is a road, even though the terrain has changed into something the map was never designed to represent. Here's where language can betray us. If someone hears that our equations break down near the beginning, they might quietly conclude, so before the Big Bang, there was nothing. But that conclusion is not science, it's a leap, a human attempt to fill silence with a story. The Planck time boundary is not evidence of nothing, it is evidence of incompleteness. It tells us that classical general relativity alone cannot describe the earliest regime, because quantum gravity effects should matter there. That is not the same as nothing existed. It is not even the same as something existed. It is simply the honest statement that the physics we currently trust for the expanding universe does not fully cover that regime. It's a boundary in knowledge, not a confirmed statement about reality. And that difference is everything, because cosmology is not allowed to confuse what we cannot yet describe with what did not exist. Those are not twins. They are not even cousins. The reason is brutally simple. We have not yet built, tested, and confirmed a full theory that unites quantum behavior with gravity in the Planck regime. Until we do, we can't responsibly claim we know what happens earlier than the boundary where quantum gravity should dominate. And again, reputable references treat this as a limit of applicability, not a verdict on existence. Caltech's NED explicitly frames the Planck time as the point where the classical Friedmann model approach in general relativity reaches its limit. Britannica frames the Planck era as a domain of extreme conditions tied to the Planck scale. So when we arrive here, we do something that feels almost unnatural for the human mind. We stop, not because curiosity stops, but because evidence stops being direct and theory stops being complete. And that pause, this disciplined refusal to pretend, is one of the most profound things science does. And if you want to feel how sharp this boundary is, picture you standing in a hallway with a door at the end. You can walk most of the way. You can see the paint texture on the walls. You can hear your footsteps echo. But when you reach the final few inches, the light above the door is dead. You can still touch the door. You can still feel the metal handle. But you cannot see what's on the other side. Not because the other side is empty, because the light you rely on is gone. That's the Planck time, a place we can approach with evidence and tested physics. And then our illumination fails, not in the universe, but in our tools. So here is what we can say, calmly, seriously, without mythology. We can describe the universe with strong confidence back through much of its early history. We can follow expansion back toward hotter, denser states. But as we near about 10 to the minus 43 seconds after the Big Bang, we reach a regime where our current theories, especially classical general relativity, are not expected to be sufficient on their own. That is where the story becomes genuinely disturbing. Because the closer we get to the beginning, the more we realize something simple. The question what happened before assumes we can keep marching backward on a time axis that behaves normally. But at this boundary, even the meaning of before starts to wobble. Because if time is part of the physical system, if it is woven into space itself, then asking what came before the beginning may not be a straightforward question at all. It may be the wrong kind of question. And once that possibility enters the room, the mystery stops being about a hidden era. It becomes about the nature of time itself. There's a moment, quiet, almost invisible, when our biggest question makes its first mistake. It happens inside a single word, before. Because before is not just a direction, it's a structure. It assumes time is already laid out like a road, stretching behind us, waiting to be walked. But modern physics does not treat time like a road. It treats time like something woven into the universe itself, stitched to space so tightly that you can't pull one away without tearing the other. And once we accept that, the question, did anything exist before the Big Bang, begins to change shape. Not because the mystery goes away, because the grammar of the mystery collapses. In everyday life, time feels absolute. A second feels like a second everywhere. A minute feels like a minute for everyone. We live as if the universe has one master clock, ticking cleanly above all things. But Einstein shattered that picture. In relativity, time is not universal in the way our intuition wants. Clocks are physical objects, and what they measure depends on motion and gravity, on the structure of space-time itself. That's not philosophy. That's the foundation behind real measurements, like gravitational time effects and the behavior of light in strong gravity. So when we ask what happened before the Big Bang, we're not asking a simple historical question. We're asking a question that assumes time is a container the universe sits inside, and relativity quietly refuses that entire picture. Cosmology still uses time, of course it does, but it uses time in a disciplined physical way. In the standard expanding universe models, there is a special notion called cosmic time, the time measured by co-moving observers, meaning observers moving with the overall expansion. In that framework, cosmic time is essentially the proper time on a standard clock carried by a fundamental observer riding the Hubble flow. This matters because it ties time to the geometry of the universe. The expansion isn't something happening within time like water boiling inside a pot. In the mathematics of cosmology, the expansion of space is described as a function of time, and that time is defined by physical clocks that belong to the universe, not by an external stopwatch hovering outside it. So cosmic time is not time everywhere in the philosophical sense. It's a chosen, physically meaningful timeline, built from the behavior of the expanding cosmos itself. And this creates a bigger problem, because if the universe defines the clock, then asking for before the universe's clock starts may not describe any physical situation at all. Imagine a story written on a long strip of paper. Each sentence is a moment. Each paragraph is an era. Now imagine the first part of the strip is blank, not because the author is hiding secrets, but because the paper itself doesn't exist yet. You can't flip to an earlier page. There is no earlier page, not unknown, not dark, just not part of the object you're holding. That is what the word before risks doing in cosmology. It asks for pages that may not belong to the book. Here's the strange part. Time isn't just an idea we talk about. In physics, time has measurable structure. We can compare clock time to coordinate time. We can define proper time, the time actually experienced along a path, measured by a clock that travels that path. This isn't poetic language. This is the reason different observers can disagree about how much time passed between the same two events, because how much time passed depends on motion and gravity, on the geometry of space-time. So time, in modern physics, is not just a background stage. It behaves, it bends, it becomes part of what the universe is. And once time is treated as a physical ingredient, we have to face the unsettling possibility. If time is an ingredient, then the universe may not have a meaningful before in the way our language assumes. Stephen Hawking put this discomfort at the center of one of his most famous themes, whether time itself has a beginning. His point wasn't that curiosity is wrong, it was that some questions are built on assumptions physics does not grant. If time is a property of the universe, if time is part of what begins, then before the beginning of time may not refer to any physical state we can describe inside the model. That doesn't prove nothing, it doesn't prove something, it proves something more disciplined. Our everyday word before may be a human instinct reaching beyond what the physics is actually defining. And this is where we have to separate two things we constantly confuse: the language we evolved to navigate days and seasons, the language the universe forces us to use when days and seasons don't exist. Our intuition was built for a small world, a world where earlier always exists, a world where before is always available. But cosmology is not describing a small world. It is describing space-time itself, and in that description, before can become a trap, because it assumes time is a container rather than a feature of the system. So the mature move in physics is not to force an answer, it is to ask whether the question maps onto something measurable, something that can, even in principle, leave evidence. And that brings us to a sharp, personal edge. If you've ever asked someone what happened before you were born, you're asking a question that makes sense because time keeps flowing whether you exist or not. But now imagine asking, what happened before the calendar was invented? Not the invention by humans, the calendar is a structure for counting days. Before the calendar, there may still be days, but the system you're using to define before doesn't apply. That's what this feels like. We're standing at the boundary where the universe may be defining the very meaning of time itself, and we're trying to push an everyday word through a doorway it may not fit through. So we don't lose the mystery, we refine it. Instead of demanding what came before, we ask something tighter. What does physics mean by time in the first place? And if time has measurable structure, if time can be stretched, warped, and defined by the universe, then the next question becomes almost unavoidable. When we say nothing, do we mean empty space? Or do we mean the deeper physical vacuum? Fields, energy, structure, things that can exist even when matter is gone. Because the moment we stop treating before as a place, we are forced to face a different word, one that sounds simple but isn't. Nothing. There's a word we trust too easily, a word that feels clean, final, absolute, nothing. We say it like it's a blank page, like an empty room, like a silence with no hidden sound inside it. But the universe does not treat nothing as a blank. It treats nothing like a state. And that difference, quiet as it seems, changes the entire shape of our question. Because if nothing is not truly empty, then asking whether something existed before the Big Bang becomes even more dangerous. Not because we found an answer, but because the language we're using is already bending. And this is where the story cracks open. Most of us carry a picture without realizing it. A picture where the universe begins inside an emptiness, like a spark in a dark warehouse. In that picture, nothing is just the absence of stuff. No light, no matter, no energy, no structure. But physics does not define nothing that way. In physics, nothing is not a philosophical void. It's usually a word people use when they mean vacuum, and in modern physics, vacuum does not mean non-existence. It means the lowest energy state of a system, the calmest state the fields can settle into. That sounds subtle, but it is not subtle at all, because once we accept that definition, empty space stops being a passive backdrop. It becomes an active ingredient. At Fermilab, one of the major centers for particle physics in the United States, they put it plainly. Physicists have realized the vacuum is not just empty space and the absence of things. Quantum physics and experimental observations show the vacuum has physical properties, including vacuum energy and fluctuations. That's a serious statement, because it means when we strip a region of space of matter, even cool it as far as we can, we do not create philosophical nothingness. We create a physical vacuum, a ground state that still belongs to the laws of nature. And those laws do not turn off. Imagine a perfectly still pond at night. No wind, no ripples, no visible motion. From far away, it looks like nothing is happening, but the pond is still there. It still has depth, temperature, surface tension, and if you drop a single pebble, the whole surface reveals what was always present. That's what the vacuum is like in physics. Not a void where rules vanish, but a quiet state that still has structure, ready to respond, ready to reveal itself. Modern particle physics is built on a framework called quantum field theory, the language used to describe elementary particles and their interactions. In this picture, particles are not tiny hard beads floating through emptiness. Particles are excitations of underlying fields, and fields are not located in space the way furniture is located in a room. Fields are closer to something that permeates reality, defined everywhere space exists. CERN, the institution behind the Large Hadron Collider, emphasizes a key implication of this. When a field has a non-zero vacuum state, it can be present everywhere. In their explainer on the Higgs, they describe how a non-zero vacuum expectation value means the Higgs field is everywhere, and its omnipresence is what allows it to affect massive particles across the universe. So even in a region with no atoms, no dust, no radiation beams passing through, the universe is not switched off. The fields are still there, and the vacuum is not nothing. It is the quietest condition those fields can take. NASA says this with striking clarity. Space is never exactly empty. According to quantum field theory, there are virtual particles that can appear and disappear tied to vacuum energy. Now, this is where we must be precise. The phrase virtual particles is often used as a mental image, a way to describe quantum behavior without dragging the viewer into heavy mathematics. The deeper point, the safe, verified point, is this. The quantum vacuum has measurable physical effects. It is not a philosophical claim, it is an experimental reality. And the most famous proof is disturbingly simple. In 1948, Dutch physicist Hendrik Casimir predicted something that sounded impossible. If you take two uncharged conducting plates and put them extremely close together in a vacuum, they should feel a tiny force, because quantum theory implies the vacuum itself contributes energy in a way that depends on the boundary conditions. Britannica describes the Casimir effect as a force arising from quantum theory, in which energy present in empty space produces a small force between objects. That's not a metaphor. That's physics reaching into a place we used to call nothing and pulling back an actual measurable consequence. And to feel how unsettling this is, we need to translate the scale. This force becomes detectable only when the plates are separated by distances far smaller than a human hair, down into micrometer and sub-micrometer ranges, where everyday intuition starts to fail. A human hair is roughly the thickness of a fine grain of sand. Now imagine shrinking that hair's width 100 times. In that tiny gap, empty space stops behaving like emptiness. It behaves like a physical environment with rules and pressure and measurable outcomes. This should be impossible if nothing meant what we think it means, but it doesn't. And now we have to separate two definitions that people constantly blend together. A total absence, no space, no time, no laws, no fields, no possibilities. Physics does not operate with this nothing, because physics requires a framework, something measurable, something definable, the lowest energy state of a system within a framework, within space-time, within fields, within laws. That physical vacuum can look empty in the everyday sense, no particles flying around, but it is not non-existence. Fermilab is careful about this distinction. The vacuum has physical properties, and quantum phenomena imply fluctuations in vacuum energy. NASA echoes the same underlying truth. Space is not exactly empty in quantum field theory. So when we say nothing in a cosmology conversation, we have to ask, do we mean the philosophical void, or do we mean the physical vacuum? Because those are not the same thing, and confusing them creates a whole universe of false conclusions. This is where people often jump. They hear that the vacuum has energy. They hear that fluctuations exist. They hear that empty space isn't empty, and then they leap to a conclusion. So, the universe came from nothing. But that sentence is a trap, because it hides a switch in meanings. If nothing means vacuum, then it is not nothing in the philosophical sense. It's a structured physical state described by laws. Laws we can test. If nothing means philosophical void, physics has no verified model that describes such a state in the way we describe fields and space-time. So we don't get to slide between meanings without paying the price. Science does not allow that kind of word magic. Not when the stakes are the origin of everything. Think about you standing in a quiet room at night. No music, no talking, no movement. It feels like silence. But if you listen closely, you still hear the room. A faint hum from wiring, the breath in your chest, the distant movement of air. Silence is not nothing. It's what remains when the loud signals stop. That's what the vacuum is like. It is not a dramatic something. It is what remains when the obvious stuff is removed. Yet the fabric of physics is still there, still humming with measurable properties. This is why cosmologists speak carefully, because when we ask, did anything exist before the Big Bang? We're not just asking about time, we're asking what kind of nothing we imagine sitting on, the far side of that boundary, and physics refuses to let nothing remain vague. CERN's descriptions of fields, like the Higgs field being everywhere due to its vacuum state, remind us that empty space is still a place where fundamental fields exist. Fermilab's explanation reminds us that the vacuum is not absence. It has physical properties confirmed by observation. Britannica's discussion of the Casimir effect reminds us that this is not just theory talk. It's grounded in effects tied to quantum physics in empty space. So we can't use casual words for cosmic questions, because casual words create casual misconceptions, and those misconceptions become the mental images that derail the entire story. So here is what we can say, calmly, without exaggeration. When physics says vacuum, it does not mean nothing exists. It means a lowest energy state with structure, governed by quantum fields, capable of producing measurable effects. And once we accept that, one of the most common pictures in popular culture becomes immediately suspect. The picture where the Big Bang was a blast into empty space, a fireball surrounded by a cosmic void, a bomb in darkness. Because if empty space is not truly empty, then the Big Bang cannot be understood as an explosion into nothing. And if that picture breaks, then we have to rebuild the mental model from the ground up, because the universe had a beginning we can trace. But but it did not begin the way our instincts keep trying to draw it. Some ideas survive not because they're true, but because they're easy to draw. We've all seen the same image: a black emptiness, a tiny spark, then a blast, matter flying outward into nothing. It feels intuitive, it feels cinematic, but it is also one of the most misleading pictures in all of science. And if we carry that picture forward, it quietly poisons everything that follows, especially the question we care about most. Because if we imagine the Big Bang as an explosion in space, then before sounds like a place we could stand, watching it happen. But that is not how modern cosmology describes it. So we have to do something uncomfortable. We have to unlearn the popular image and rebuild the mental model from the ground up. The Big Bang was not a bomb. It was not a fireball erupting from a single location. NASA's Dr. John Mather, Nobel laureate and a senior scientist tied to the James Webb Space Telescope, states it directly. The Big Bang did not occur at a single point in space as an explosion, and it's better thought of as the simultaneous appearance of space everywhere in the universe. That one sentence detonates the old picture, because if it wasn't a single point in space, then the Big Bang was not an event that happened somewhere. It was an event that happened to space itself. When we imagine an explosion, we automatically imagine a center, a point you could mark, a place you could travel to, and we keep asking, where did it happen? Smithsonian, drawing on expert guidance from the Harvard and Smithsonian Center for Astrophysics, summarizes the modern view bluntly. Scientists don't think the Big Bang happened at a single location in space. It happened everywhere at once. That doesn't mean everywhere we can see. It means everywhere that existed. Every region of space was once hotter and denser than it is now, and the expansion is the story of that entire fabric stretching. So the center isn't hidden, it's not far away. It doesn't exist in the way an explosion center exists. The center is a symptom of the wrong metaphor. Imagine we are standing in a kitchen while bread is baking, not a loaf in a pan. Bread rising in every direction, like dough expanding from within itself. Now, imagine tiny raisins inside it. As the dough rises, every raisin sees every other raisin moving away. No raisin is the center, and no raisin can point to an edge where the bread is expanding into empty air, because the growth is happening everywhere inside the loaf. That's closer to the expanding universe than any fireball in darkness. Not perfect. No analogy survives contact with the cosmos. But it breaks the most dangerous illusion, the idea that expansion needs a surrounding emptiness to expand into. This is where the story gets sharper. We often talk as if the universe is a thing inside a bigger container, like a balloon inside a room. But the Big Bang model is not space expanding into space. It is the expansion of space itself, the growth of distances between galaxies at cosmic scales. Harvard's Center for Astrophysics has an old but clear way of pushing against the wrong picture. During the Big Bang, there was no empty space surrounding a clump of matter. Space itself was filled more or less uniformly with matter and energy, with no center of attraction. So when we say the universe expanded, we are not imagining matter rushing outward into a pre-existing void. We are describing the way the geometry of the universe evolved, distances growing as the cosmos cooled and structure formed. And this matters because it rescues us from a common misunderstanding. If there is no outside, then before doesn't behave like it does in everyday life. Explosions have a special feature. They have an after that spreads into a where, a shock wave into an environment. But in modern cosmology, the Big Bang is not a shock wave moving through space. It's the early, hot, dense state of the universe, the earliest era we can meaningfully describe with tested physics and observation, and the subsequent expansion and cooling of space itself. That's why the cosmic microwave background, the CMB, matters so much. It's not light from a point source. It's a sky-filling afterglow, present in every direction, consistent with an early universe that was hot everywhere, not a blast radiating outward from a central location. When we hold the CMB in mind, the explosion picture becomes difficult to maintain, because explosions leave asymmetries. The CMB is remarkably uniform, exactly the kind of relic you expect from a universe that was once hot and dense as a whole. So why does the wrong picture persist? Because our brains evolved in a world where event means something happens at a place. A lightning strike, a volcano, a bomb. We are built to localize, but cosmology forces us to think in a different category, an event that is not happening in space, but happening to space. And that is why language becomes dangerous here. Big Bang is a dramatic name. It makes us imagine sound, shrapnel, a fireball. Even scientists have noted how the words themselves encourage the misconception. So our job, if we want to ask honest questions, is to keep dragging our imagination back to the physical meaning. Expansion of space. Everywhere at once, no edge, no center, no outside. Now place you inside it, not as an observer outside the universe, because there is no outside in this model. Put yourself inside the expanding cosmos, on any galaxy, at any location. From there, you would see other galaxies receding, and the farther they are, the faster they appear to recede, because the stretching accumulates with distance. You wouldn't be watching a fireball move away from a center. You would be watching distances grow, quietly, relentlessly, because the stage itself is changing shape. That's the correct discomfort, not the drama of an explosion, the eerie calm of geometry evolving. So we reset the mental model like this. The Big Bang was not a localized blast. The universe did not expand into empty space. The center is not a location. It's a misconception imported from explosions. And once we see that clearly, the question changes. Because if the Big Bang is not an explosion story, then it isn't an origin scene we can simply visualize. It becomes something colder and more disciplined, a boundary where our models and observations remain strong, and beyond which we must separate what we can test from what we can only imagine. There's something we do, almost without noticing. When we reach the edge of knowledge, we decorate it. We take a hard boundary, and we paint a door on it. We call it an origin story, a beginning scene, a moment we can imagine like a memory. But the universe doesn't care how much we want a clean narrative. It only responds to what can be tested. And this is where the mystery becomes sharper, not softer, because the Big Bang is often treated like an answer. But in modern cosmology, it's closer to a limit, a boundary where our models still hold, and then the ground under them begins to shift. In human life, origin usually means a story with a cause, a spark, a choice, a first domino. But in science, origin is not a mood, it's a claim, and claims have a price. They must leave fingerprints in the world. So we need to separate two things that sound similar but behave nothing alike. One is an origin story, the other is a testable model. An origin story gives us a satisfying picture. A testable model gives us a risky prediction. An origin story feels complete. A testable model admits where it stops. And cosmology, serious cosmology, is built on the second one. Meaningful doesn't mean emotionally meaningful. It means something colder. A meaningful scientific question is one that can, at least in principle, be confronted by evidence. That is why the scientific method is not a list of steps like a recipe. It's a discipline, a way of letting reality push back. And when reality can't push back, when no possible observation could rule the claim out, science becomes careful, not dismissive, not arrogant, just careful. This is why philosophers like Karl Popper became famous for emphasizing falsifiability. the idea that scientific claims expose themselves to being wrong. Not because scientists love being wrong, because being wrong is the only way a model proves it is connected to the world. And cosmology, despite how grand it sounds, still lives under this rule. Imagine we're standing on a shoreline at night. We can see the waves nearest our feet, clear, detailed, undeniable. Farther out, the ocean becomes darker. We can still infer it's there, because the pattern of waves tells us something about deeper water. But eventually the darkness wins, not because the ocean ends, but because our eyes do. That's the difference between a story and a model. A story pretends we can see the whole sea. A model tells us exactly how far our light reaches and what we're doing when we speak beyond it. Here's the strange part. Science is not threatened by unanswered questions. It's threatened by pretending. If we ask, what was the universe like when it was extremely hot and dense? That question can be tied to evidence, because that early state leaves relics. For example, NASA states that the cosmic microwave background is the oldest light we can observe, a direct observational pillar for our early universe picture. ESA's Planck mission describes the cosmic microwave background as relic radiation from the Big Bang, mapped across the whole sky with high sensitivity. Those are not stories, those are measurements. But when we ask, what happened before the Big Bang? We're often asking something that may not map cleanly onto testable evidence, at least not with the physics we currently have. That doesn't make the curiosity unscientific. It makes the certainty unscientific. It means the honest answer might be, we don't yet know how to connect that question to observation without smuggling assumptions in. And that honesty is not a weakness. It's the entire spine of the scientific approach. Cosmology is sometimes accused of being just theory. But cosmology is one of the most data-driven sciences we have, because it doesn't build one single argument, it builds a cross-examination. Expansion is tested against galaxy redshifts, large-scale structure, and distance measurements. The early hot universe is tested against the cosmic microwave background and the observed abundances of light elements. And the strength comes from the fact that these are different kinds of evidence that converge on a coherent picture. The Particle Data Group's Big Bang Cosmology Review is an example of how carefully this is treated. It doesn't read like mythology. It reads like accounting. What is measured, what is inferred, what parameters fit, what tensions remain. And that last phrase matters. Tensions remain. Cosmology does not pretend the universe is fully solved. It quantifies uncertainty. It writes numbers with error bars. It argues openly about where measurements disagree. That is not the failure of cosmology. That is the muscle of cosmology. There's a particular kind of discipline in how scientists talk about the early universe. They don't say, "This is what happened," like a narrator describing a witnessed event. They say, "This is the model that best fits the evidence we have." NASA's framing is careful. The cosmic microwave background is the oldest light we can observe, meaning there is a limit to our direct observational access. ESA's Planck framing is careful. It studied the relic radiation left over from the Big Bang with high precision, meaning the claim is anchored in an observed signal, not in imagination. So we can speak confidently about much of the early timeline. But confidence in science is not a vibe. It is earned by the ability to confront the model with reality. This is where our expectations have to mature. The Big Bang model is not, in itself, a complete origin story. It is a description of an expanding universe that was once hotter and denser, supported by multiple lines of evidence. But it is not a final answer to why there is a universe, or what, if anything, precedes the earliest regime our physics can describe. NASA's overview of the Big Bang emphasizes what we can observe and trace, like the oldest light, rather than claiming an absolute description of the first moment. And the Particle Data Group review is blunt in its own way. The model is powerful, but it is still a model, and it is constrained by physics we can test and by regimes where we know our current theories are incomplete. So the Big Bang sits in a strange position. It is one of the most supported frameworks in all of science, and it is still a boundary. It explains an enormous amount, but it is not the same thing as explaining everything, and this is exactly where people get uncomfortable, because we want a single sentence that ends the mystery. But the universe does not offer that sentence, and if we're honest, this is where you can feel the tension, because part of you wants to stand outside the universe and watch it begin, like a match struck in darkness. But there is no outside observer in the model. There is only us, inside the system, reading relics, measuring patterns, reconstructing history from light that has been traveling for billions of years. We are not watching the beginning like a memory. We are detecting it like a whisper, faint, ancient, and unbelievably disciplined. That's why the question is so heavy, not because it's mystical, because it forces us to accept what it means to be a creature inside the thing it's trying to understand. There's a temptation when we hear the word limit to hear surrender, but limits are not surrender. They are boundaries that keep us honest. In science, a limit is a statement like, this is where our evidence ends. This is where our tested equations stop being reliable. This is where our language becomes dangerously metaphorical. That kind of limit is not a wall built by ignorance, it's a wall built by integrity. It's the difference between saying, we don't know, and pretending we do. And it's also what makes progress possible, because once we name the boundary precisely, we can build better tools to push it. So when we talk about cosmic origins, we have to keep repeating one quiet rule to ourselves. A model is not a story. A model is a disciplined agreement between mathematics, measurement, and humility. A story wants closure. A model wants constraints. A story wants to answer why, as if the universe owes us motives. A model answers how only as far as evidence will carry it, and no farther. And this changes how we should hold the Big Bang in our minds, not as a dramatic first scene, but as the earliest boundary where our best-tested cosmic description remains anchored to observation, especially through relics like the cosmic microwave background. So we arrive at a calm, unsettling truth. The Big Bang is not a full explanation. It is a boundary of description, a line where the universe becomes so extreme that our models must be handled with care, and our imagination must be kept on a leash. And once we accept that, a deeper question rises. Not what story do we like, but something colder, something more honest. What exactly can observation ever reach? Because even if our theories were perfect, even if our equations were flawless, there is still a limit written into the universe itself, a horizon, a boundary of visibility, a point beyond which the cosmos may be forever hidden, not because it isn't there, but because no signal can ever arrive to tell us. And that's when the mystery becomes truly sharp. There are places in the universe we will never reach, not because our rockets are weak, not because our telescopes are blind, but because reality itself has a speed limit. Light is the fastest messenger we have, and light is not generous. It does not carry information instantly. It drifts. It takes time. It arrives late. So every time we look into the night sky, we are not seeing the universe as it is. We are seeing the universe as it was, stamped into photons that have been traveling for billions of years. And that sounds poetic until we realize what it means. It means there is a hard boundary, an edge of visibility, where the universe is not merely dim, it is silent. Not because nothing is there, but because no signal has had enough time to reach us. That boundary has a name, a horizon, and horizons are where certainty ends. Imagine you're standing in a city during a blackout. No streetlights, no windows glowing, only darkness. You lift a flashlight. Right in front of you, the world becomes real again. Edges, shapes, depth. A few steps farther, the beam fades into shadow, and then it simply stops. Not because the street ends, not because the buildings vanish, but because your light cannot reach them. That is the observable universe, not the whole cosmos. Just the part our flashlight, the speed of light across the age of the universe, has been able to touch. The universe is about 13.8 billion years old, a number so large it almost stops feeling like a number. But the important detail is not the age, it's the consequence. If nothing can travel faster than light, then there is only so far any information can go in 13.8 billion years. That is why observable doesn't mean our technology is good enough. It means physics allows it. And because space has been expanding while that light was traveling, the edge of the observable universe today is much farther than 13.8 billion light years. Calculations show it's more than 46 billion light years in any direction, about 93 billion light years across. That number is almost cruel, because it means the oldest light we see has been traveling for nearly the entire age of the cosmos. And the place it came from is now unimaginably farther away than the distance the light actually traveled. The universe is not just big, it is running away while we try to measure it, and this creates a deeper mystery. Because even within that vast sphere, there are eras we cannot see. We often talk about seeing back in time as if the past is a clear hallway and all we need is a strong enough telescope. But the early universe wasn't transparent. It wasn't a quiet stage waiting to be observed. For the first hundreds of thousands of years, the cosmos was a hot, dense plasma, charged particles and light trapped together, scattering constantly. Light couldn't travel freely. The universe was, in a very literal sense, opaque. So even if we built a perfect telescope the size of a galaxy, there still would not be a clean view, because before a certain moment, there is no light traveling through space the way we imagine it. And then, something changed. The universe expanded, cooled, and allowed electrons and protons to settle into neutral atoms. Space became transparent, light was finally released, and that ancient glow still exists, still washing across the cosmos, still arriving at Earth. NASA calls it the cosmic microwave background, the oldest light we can observe. ESA describes it as the furthest back in time we can explore using light, formed about 380,000 years after the Big Bang. And that is a terrifyingly sharp boundary, because it means our most direct visual access to the early universe stops, not at the beginning, but at the moment the universe finally stopped hiding its own light. Let's hold that number in our hands for a moment. 380,000 years. Compared to 13.8 billion years, it sounds almost small, but it isn't small in human terms. If we compress the entire age of the universe into a single calendar year, those first 380,000 years would still be the first minutes after midnight on January 1st. Everything before that is not darkness because nothing existed. It's darkness because the universe was too hot and too dense for light to move. So the cosmic microwave background is not just old light, it is a wall, a frozen surface of last scattering, a fossil boundary where the universe first became transparent enough to reveal itself. And beyond that wall, we are forced to infer, we are forced to model, and we must admit where observation becomes indirect. But then it gets stranger, because some things are hidden, not by opacity, but by permanent distance. Even if the early universe had been transparent from the first instant, we would still face a limit, because the universe has only had a finite amount of time to send us information. This is where the horizon becomes more than a metaphor. The observable universe is the region from which any signal could have reached us since the universe began. Outside that region, events may be happening right now. Galaxies may exist, stars may be burning, civilizations could be rising and collapsing in darkness. But if their light has not had enough time to arrive, then for us, they do not yet exist in observational reality. And this is the most unsettling part. There is no single center of that sphere. Every observer has their own horizon. The universe is not arranging itself around Earth. We are simply trapped inside our own causally reachable bubble. This isn't philosophy, it's geometry, carved by the speed of light. And it means something brutal. There are truths the universe may contain that we cannot access, not because we are ignorant, but because we are late. And if we're honest, this is where you feel the weight of it. Because part of you wants the universe to be like a room you can walk across. If you just try hard enough, you'll reach the far wall. But the universe isn't a room, it's an expanding horizon. The far wall moves. The messages arrive delayed, and some messages will never arrive at all. Not because the universe is cruel, but because it is physically consistent, and that consistency has consequences. When we say there are eras we can't observe, we have to be precise, because precision is the only guardrail against turning cosmology into mythology. The cosmic microwave background is our earliest light-based snapshot. Before that, the universe is a plasma fog where photons were trapped. So what could carry information from earlier times? In principle, other messengers exist. Neutrinos, for example, barely interact with matter, and gravitational waves can travel through regions that light cannot. But here is the discipline. In principle is not the same as in evidence. We can talk about these messengers as physical possibilities, but unless we can measure them with the same kind of rigor we measure light, we do not get to pretend they are already part of our confirmed observational record. So right now, for the early universe, light gives us a boundary, and beyond that boundary, we are building the best possible reconstruction from indirect clues. This creates a new problem, because human instinct treats unseen as not there. But science has a stricter rule. There is a sentence that sounds simple, almost boring, but it has saved science from countless disasters. Absence of evidence is not evidence of absence. If we don't observe something beyond our horizon, that does not mean it doesn't exist. It means we cannot test it with our current access to information. The horizon is not a verdict. It's a limit on what the universe has allowed to reach us. And the cosmic microwave background is not a curtain hiding a blank stage. It's a curtain hiding a region of extreme physics, real, violent, primordial conditions where our equations are tested to their limits. ESA calls the cosmic microwave background the furthest back we can explore using light. NASA calls it the oldest light we can observe. Those are not poetic lines. They're carefully worded boundaries. They're scientists telling us where observation ends. And the difference matters, because once we cross from observation into speculation, we stop doing cosmology. We start doing comfort. Cosmology is sometimes portrayed as a field that makes huge claims from almost nothing, but the truth is harsher and far more impressive. Cosmology is a field that makes huge claims only when multiple independent lines of evidence agree, and it stays quiet when they don't. The horizon forces humility because it forces honesty. It tells us we can measure the cosmic microwave background, we can map its tiny temperature variations, we can extract information about the early universe from it, but we cannot claim direct visibility into times before the universe became transparent to light, and we cannot treat before our horizon as a place where any statement is automatically true. A boundary does not give us freedom, it gives us responsibility. Here's what makes this truly disturbing. The horizon is not just an edge in space, it's an edge in time, because every observation is delayed, every photon is old, even sunlight is 8 minutes late. The glow of the moon is over a second late. The nearest star beyond the sun, Proxima Centauri, is more than 4 years late, and the oldest light we see is almost the entire age of the cosmos late. So we are never looking at now, we are looking at a layered archive, a cosmic fossil record written in light, and some parts of that archive do not exist for us yet, and may never exist for us. Not because we are small, but because we are inside the system, obeying its rules. All of this circles back to the question that keeps haunting the human mind. Did anything exist before the Big Bang? But now we can feel the trap hidden inside the question, because before we can even speak about before, we have to admit what our observations can and cannot do. Observations can carry us far, but they do not carry us infinitely far. They hit the horizon, they hit the wall of the oldest light, they hit the limit set by the age of the universe and the speed of light. And once we reach those limits, we must change how we speak, not softer, not vaguer, more precise. Because the next step is not storytelling, it is something colder and more careful. How do we talk about the unknown without lying? How do scientists frame unanswered questions so they remain tethered to evidence instead of drifting into myth? Because that is the next boundary. Not in space, not in time, but in language. And the way we handle that boundary decides whether we are doing science or just telling ourselves a story. There's a moment in every cosmic story where our instincts betray us. We feel the pull of the unknown, and we want to fill it. We want a sentence that closes the wound. We want a picture that makes the darkness feel less threatening. But the universe doesn't reward comfort. It rewards discipline. Because in science, the unknown is not an invitation to invent. It is a warning sign, a line on the road where the headlights stop working, and where every confident claim becomes dangerous. And this is the part most people miss. Science is not powerful because it has answers. Science is powerful because it has rules for what counts as an answer. Imagine we're standing in a courtroom. Not a dramatic one, not loud, just quiet, cold, procedural. A claim is placed on the table, and the judge asks one question. What would make this claim fail? Not, what would make it sound beautiful? Not, what would make it feel right? Not, what would make it go viral? What would make it wrong? That single question is the difference between a story and a scientific statement. And when we talk about before the Big Bang, that question becomes the door we either walk through or refuse to. Cosmology deals in extremes, a universe nearly 13.8 billion years old, distances that make our language feel small, physics that stretches until it trembles. And yet, despite that scale, cosmology is not allowed to drift into poetry alone. It has to stay chained to evidence. So when scientists speak about the unknown, they do it with a strange kind of restraint. They divide what we know into categories: what we observe directly, what we infer carefully from observation, what we model because the physics is consistent, and what we do not claim because the evidence cannot reach. NASA says the cosmic microwave background is the oldest light we can observe. That statement is not just informative, it's a boundary line. It's science saying, here is where our direct visual record begins. And everything beyond that point becomes a different kind of conversation. Not less serious, more constrained. When we hear the word model, we often imagine something flimsy, a rough sketch, an approximation, a guess dressed up in math. But in physics, a model is something else. A model is a disciplined machine. You feed it assumptions, explicit, written down, testable, and then you demand outcomes. If the outcomes match multiple independent observations, the model survives. If they don't, it collapses. That collapse is not failure. That collapse is the system working, because the goal isn't to protect the model. The goal is to protect reality from our imagination. This is why scientists can talk about the early universe with confidence in some places and deep caution in others, because they are not building a myth. They are building a structure that must carry weight. Here is the uncomfortable truth. Science cannot treat every question as equal. Some questions are meaningful because they can be tested. Some questions are meaningful but not yet testable. And some questions, no matter how haunting, cannot currently be answered without stepping outside science. This is where the idea of falsifiability enters. The philosopher Karl Popper argued that scientific claims must be exposed to the possibility of being proven wrong, that a claim must risk collision with observation, not because science loves negativity, because science refuses to confuse belief with knowledge. A claim that cannot, even in principle, be tested is not automatically false, but it is not scientifically established. And cosmology lives on this knife edge every day, because the early universe is a place where data thins out and temptation grows. Falsifiability sounds like a philosophy word until we feel how it operates in the real world. In cosmology, it looks like this. If the universe truly expanded from a hotter, denser past, then we should see relics of that past, not vague relics, specific ones, measurable ones. We should see patterns in the sky that no local modern process can fake. We should see the cosmic microwave background. And we do. NASA describes it as the oldest light we can observe. That matters because it wasn't guaranteed. It could have been absent, or structured in a way that contradicted the Big Bang framework. Instead, it exists. It's measurable. It's mapped. And when evidence like that appears, the model becomes more than a story. It becomes a survivor, a theory that has endured pressure. But then comes the sharper question. What happens when we ask about regions the evidence cannot touch? This is where science becomes almost morally strict, because the unknown is not a playground. If we say we don't know what happened earlier than the oldest observable light, that does not mean the rules are gone. It means we have reached a zone where claims must change their status. They become hypotheses, not conclusions. They become research programs, not settled facts. They become careful language. This is why serious cosmologists speak differently than internet arguments do. They will say consistent with, constrained by, supported by, disfavored by, not because they're weak, because they know the cost of pretending. The universe is not obligated to align with human intuition, and when the evidence runs out, pretending certainty is not bravery, it's theatre. Science has a reputation for confidence, and yes, when something is measured cleanly and confirmed repeatedly, science speaks with strength. But the deeper truth is that science is built around uncertainty, not the romantic kind, the quantified kind, the kind you write down, the kind you carry openly. The national academies describe how scientific measurements carry uncertainty, those error bars that show the limits of what a measurement can claim. This matters because cosmology is not a single observation. It is a web, a structure built from independent measurements that must agree. When they do agree, the structure becomes strong. When they don't, scientists don't pretend. They argue, they refine, they remeasure. Because uncertainty is not a weakness in science. It is the honesty mechanism. This is the part that can feel cold, because humans want closure. We evolved in a world where unanswered questions meant danger, a rustle in the grass, a shadow at the edge of firelight. Our brains are designed to complete patterns, to finish stories. But the cosmos punishes pattern completion when it goes beyond evidence. That punishment can be subtle, a model that predicts the wrong abundance of elements, a map of the cosmic microwave background that refuses to match your preferred story, a measurement that will not bend. Cosmology does not allow us to believe our way into truth. It forces us to earn it. And here is where you can feel the pressure. Because when we ask, did anything exist before the Big Bang? We are not only asking a scientific question, we are asking an emotional one. We are asking for a kind of reassurance that reality has a flaw, that existence has a clean origin we can understand. But science cannot promise reassurance. Science can only promise one thing. It will not knowingly lie to make us feel better. And that is why its language sounds restrained, because restraint is the price of being real. So how do scientists avoid asserting claims without evidence? They do it in a few disciplined ways. They separate observation from extrapolation. They say, here is what we measure, and here is what our equations suggest if we extend them. And they openly admit where equations lose authority. This isn't evasive. It's responsible. The Particle Data Group, assembled by an international community, hosted through CERN, publishes detailed reviews on Big Bang cosmology that emphasize constraints, uncertainties, and the evidence behind different parts of the model. That tone, careful, technical, reluctant to oversell, is the signature of real science. Because if something is not securely supported, the claim stays provisional. Not forever. Just until the universe gives up more evidence. There's a word that sounds harmless. But it is one of the most dangerous words in the entire conversation about origins. Before. Because before is a word from everyday life. Before breakfast, before sunrise, before childhood. It assumes time is already there, like a road. But in cosmology, time is not simply a background stage, it is part of the physical system. So when we ask, before the Big Bang, we are often smuggling in an assumption that time existed in the same way it exists now. Science is cautious here because science has seen this mistake before. Language can trick us. It can make an untestable question feel like a simple one, and this is why cosmologists don't just chase answers. They also interrogate the question itself. There is a kind of mystery that science respects. Not the mystery of anything is possible, the mystery of something is constrained but not yet known. That mystery is productive. It produces experiments, missions, measurements. It produced the mapping of the cosmic microwave background. It produced the patient, decades-long refinement of cosmological parameters in scientific reviews. This is what scientific mystery looks like. A question held tightly enough that it doesn't dissolve into fantasy. A question surrounded by boundary lines. A question that stays honest. And that honesty changes how we approach the deepest problem of all. Because, did anything exist before the Big Bang? Is not a question science answers with one bold sentence. Science answers it by narrowing what can be claimed and refusing to pretend beyond that. So now, the ground under our feet changes, not because the evidence has vanished, but because we have reached the edge of what evidence can certify. We have learned how science speaks when it is strong, and how it speaks when it is unsure. We have seen that models are not guesses, that falsifiability is the price of meaning, that uncertainty is carried openly, not hidden, that the oldest light we can observe marks a boundary, not a full explanation. And now we're standing at the edge of the question again, but we're standing there differently, less hungry for comfort, more loyal to truth, because once we understand how science talks about the unknown, there is only one final move left, to say, with absolute precision, what we can honestly claim and what we cannot. There's a moment in every honest investigation when the room goes quiet, not because we ran out of imagination, but because the evidence stops. And with the Big Bang, that silence is not poetic, it's empirical. We can say with real confidence that the universe has a measurable history, a history written into light, a history that still reaches us, after travelling for billions of years, like a message in a bottle crossing a black ocean. But the most unsettling part is this: the deeper we go, the more precise our knowledge becomes, right up until it doesn't. And that edge, where our best physics becomes a question mark, is where the words before the Big Bang begin to misbehave. We do not hold the Big Bang as a belief. We hold it because the universe keeps confessing. When astronomers measure distant galaxies, they find a simple, disturbing pattern. The farther away a galaxy is, the faster it's moving away from us. That isn't philosophy. That's data taken, with telescopes repeated across decades and refined by teams across NASA, ESA, and universities around the world. And when we trace that expansion backward, carefully, mathematically, and with humility, the story doesn't drift into vague myth. It sharpens. The universe was denser before, hotter before, more compressed, more violent, more unforgiving, not in one corner of space, everywhere at once, because it was space itself that was different. And this isn't one fragile clue, it's a convergence. 3 independent pillars hold up the early universe picture. First, expansion, seen in galaxy redshifts. Second, the cosmic microwave background, an ancient afterglow still filling all directions. Third, the light element abundances, especially hydrogen, helium, and deuterium, matching what Big Bang nucleosynthesis predicts. 3 different kinds of evidence, 3 different physical processes, all pointing back toward the same early conditions. That's not assumption, that's the universe repeating the same story in 3 different languages. Now, let's get painfully specific. The cosmic microwave background, often called the CMB, is not a metaphor. It is real radiation. It is the cooled remnant of a time when the universe was so hot and dense that light couldn't travel freely. Photons kept crashing into charged particles, trapped in a glowing fog. Then, about 380,000 years after the Big Bang, the universe cooled enough for atoms to form, and light finally slipped free. And that light has been traveling ever since. Today, that ancient glow has cooled to just a few degrees above absolute zero, about 2.725 Kelvin, measured with extraordinary precision by missions like COBE. It's hard to emotionally feel 2.7 Kelvin. So imagine it this way. Picture a winter night so cold your breath becomes a visible cloud. Now, imagine cooling the entire sky, not to freezing, not to Antarctic, cold, but to a temperature only a whisper above the coldest possible state matter can reach. And that faint, uniform chill is the oldest light we can directly observe. We are not guessing that it exists. We are bathing in it. But light is only one kind of relic. The early universe also left chemistry behind. In the first minutes after the Big Bang, when the cosmos was still unimaginably hot, protons and neutrons collided and combined, forming the first light nuclei. This period, called Big Bang nucleosynthesis, didn't make planets or people. It made the simplest building blocks, most of the hydrogen, much of the helium, and trace amounts of deuterium and lithium. And when scientists measure primordial element abundances, especially deuterium in distant, nearly pristine gas, they find values that match what Big Bang nucleosynthesis predicts within the framework of well-tested particle and nuclear physics. This matters because it's an independent witness. The CMB is light. Nucleosynthesis is chemistry. 2 different messengers telling the same story. The universe was once in a hot, dense early state. That is as close to a scientific confession as the cosmos ever gives. Now we confront another hard truth. We can estimate how old the universe is, not by intuition, by combining multiple measurements, especially the detailed structure of the cosmic microwave background, with a model that has survived relentless testing. Results from the Planck mission place the age at about 13.8 billion years. 13.8 billion years. If we compress all of that into a single calendar year, human civilization, the entire story of cities, writing, empires, and science, shows up in the final minute before midnight on December 31st. Most of the universe's story happened with no eyes to witness it, no minds to name it, only physics, only consequence. But here's where the honesty becomes uncomfortable. All of this evidence, redshift, the CMB, element abundances, does not give us a verified picture of before. It gives us something both powerful and limited, a description of how the universe evolved from an early hot, dense state into the cosmos we see today. And the closer we push toward the beginning, the more extreme the conditions become, until our current theories no longer agree with each other in a complete way. General relativity, Einstein's theory of gravity, is astonishingly accurate on cosmic scales. Quantum physics is astonishingly accurate on the smallest scales. But when the universe becomes both cosmically dense and quantum-dominated, we are left with a fracture line. That is not a poetic failure, it is a technical boundary. And beyond that boundary, we do not have verified evidence that describes what before means, or even whether before is a physically meaningful question in the way our brains want it to be. Science is sometimes portrayed as confident, to the point of arrogance. The truth is almost the opposite. In its best moments, science is disciplined humility. A claim must be anchored to observation. A model must survive attempts to break it. This is why philosophers of science like Karl Popper emphasized falsifiability, the idea that a scientific claim has to be vulnerable to being proven wrong by evidence. We don't protect a theory by believing harder. We protect it by attacking it with reality. And the Big Bang model, this picture of cosmic evolution from a hot, dense early state, has survived because reality keeps failing to overthrow it. But notice what science does not do. It does not turn silence into certainty. When the evidence fades, science does not fill the darkness with a confident story just to ease our discomfort. It marks the boundary, and it stops. So what do we honestly know? We know the universe is expanding, and that expansion points back to an earlier, denser state. We know the universe carries an afterglow, released when light first traveled freely, still visible today as the CMB. We know the earliest chemistry matches a universe that once ran at temperatures and densities beyond anything we can recreate on Earth. We know the universe is about 13.8 billion years old, based on measurements that cross-check each other with remarkable consistency. And we also know this: no verified evidence currently describes a before the Big Bang. Not before as a place, not before as a time, not before as a physical state we can point to with data. And that means we cannot confirm existence, and we cannot confirm non-existence. We are not allowed, by our own rules of honesty, to claim either. And this is where you can feel the strain between the universe and the human mind. Because your intuition was built for a world where every story has a before, every fire has a match, every river has a source upstream. But the universe is not obligated to match the shape of our instincts. It only offers what it offers: evidence, limits, and the courage to admit the boundary when we reach it. We pause here, not with a conclusion, but with an honest boundary. The Big Bang is not a myth of creation. It is the earliest chapter our evidence can currently read aloud. And beyond that, there is a silence we have not yet learned how to translate. Not because the universe is empty, but because our knowledge, right now, has an edge. And what waits on the far side of that edge is not a story we can responsibly tell, only a question we can responsibly carry. But that question has one last twist, because if time itself is part of the story, then the final mystery isn't what happened before, it's whether before ever belonged here at all. There's a strange moment that happens when we stare at the universe long enough. At first, it feels like we're learning facts, ages, distances, temperatures, signals. But then quietly, the facts start to change us. Because the deeper we push backward toward that earliest readable moment, the more the universe stops behaving like a story with a familiar timeline, and starts behaving like something older than our instincts. We want a simple sequence. We want a door and a hallway and a room behind it. We want before. But the universe does not promise us that kind of comfort. And the closer we get to the Big Bang, the more the word before begins to tremble. Not because we're afraid, but because the word itself may not fit the shape of reality. Imagine you're standing in your kitchen late at night. The house is asleep, the air is still, and the only light is the soft glow from your refrigerator door as you open it. Inside, everything is visible, but only because the light is there. The shelves, the shapes, the edges, the things you can name. Now imagine the light fades slowly, steadily, until it becomes too weak to reveal anything. The refrigerator is still there. The room is still there. Reality hasn't vanished, but our ability to see it has reached a boundary. The early universe is like that, not a place where the universe stops, a place where our evidence stops speaking clearly, and the Big Bang sits at that threshold, the earliest moment our instruments, our equations, and our observations can currently translate into meaning. When we say the Big Bang, we are not pointing to a fireball in empty space. We are naming a condition, a universe that was once hotter, denser, more uniform, a universe so tightly packed with energy that atoms could not survive, light could not travel freely, and matter and radiation were locked together like fog and heat in a sealed room. We can speak about that era because the universe left traces. They are faint, they are ancient, but they are real. A background glow that still fills the sky, a cosmic after-image cooled to just a few degrees above absolute zero. The expansion of galaxies that pull space outward like a slow, relentless tide. The chemical fingerprints, hydrogen, helium, and a whisper of lithium that match what early universe physics says should have formed in the first minutes. This is not mythology. This is evidence. And it tells us something both beautiful and disturbing. Our universe has a past we can reconstruct, but only up to a point. Before is a word built from human life. It belongs to kitchens and calendars, to footsteps down hallways, to cause and effect in a world where time behaves like a straight line. But in modern physics, time is not just a background. Einstein showed us that time is stitched to space, woven into a single fabric where motion and gravity can stretch it, compress it, and bend it. Time can run differently near a massive object. It can drift at different rates for different observers. That alone should make us cautious, because if time can be stretched and shaped, then time can also be part of what begins. And once we accept that possibility, the question changes. Not what happened before the Big Bang, but something colder, something sharper. If time itself is tied to the physical universe, if time is a feature of the cosmos, not a container around it, then, before the beginning of time, may not be a real location. It may be a grammatical illusion, a habit of language, trying to force reality into a human shape. There's a very common mistake people make at this edge. We reach the earliest moment science can describe, and we assume that beyond it is emptiness. But that is not what the evidence says. The evidence says something more honest. We don't know, because the breakdown is not necessarily in the universe. It is in our tools, our best. Theories, general relativity and quantum physics are both extraordinarily successful, but when we push them to the extreme conditions near that beginning, they stop agreeing. Gravity becomes violent and absolute. Quantum effects become unavoidable, and the mathematics that guides us through nearly everything else begins to fail. That failure is not proof of a void, it is proof of a limit, a sign that our understanding is incomplete. It's like trying to describe the ocean using only the physics of raindrops. The moment the storm becomes a wave, our language breaks. And that is why careful cosmologists do not stand at the edge and declare what lies beyond. They stand there and measure the edge itself. Here is the hardest truth to live with. There may be no earlier in the way we mean it. Our minds are built to think in sequences because we evolved inside sequences. We learned time by watching shadows move. We learned cause and effect by dropping stones and hearing them strike the ground. We are animals shaped by days and nights, by seasons, hunger, and heartbeat. We did not evolve to understand a universe where the word before might be meaningless. So when we ask, did anything exist before the Big Bang? We may be asking a question that assumes something false, that before is always available, that time is always there, waiting like an empty road. But physics does not guarantee that road. It only tells us what we can test. And right now, what we can test has a beginning, not because reality is obligated to start, but because our evidence has a first readable page. And this is the moment that can feel almost personal. Because if you imagine asking the universe for the one thing we crave most, a clean origin, a clear what came first, the universe does not answer with a story, it answers with a boundary. Not a wall built to keep us out, but a horizon that reminds us what science is. Science is not a machine that manufactures certainty. Science is a discipline of restraint, a method that says, again and again, show us the evidence, show us what can be tested, show us what survives contact with reality. And when the evidence ends, science does not fill the silence with invention, it holds the silence. So what can we honestly say here at the end? We can say the Big Bang marks the earliest era we can currently describe with confidence. We can say our universe has been expanding for billions of years, about 13.8 billion by our best measurements. We can say the cosmic microwave background is a real signal, a cooled echo from when the universe became transparent to light. We can say the abundance of light elements matches what the early universe would produce. We can say our models have earned their place, not through belief, but through survival. And we can say something else, equally important. We have no verified evidence that describes a before, not because we've proven there was nothing, not because we've proven there was something, but because the question may be reaching past the meaning of time itself. This is where the story becomes philosophical, not in the sense of speculation, but in the sense of accepting what the evidence forces us to accept. There is a kind of humility written into the cosmos, not the humiliation of ignorance, but the humility of accuracy. We are allowed to say we don't know and still be standing on solid ground. We are allowed to stop at a boundary and still be speaking truth. Because the goal was never to have an answer for every question. The goal was to learn the difference between questions the universe can answer and questions that are shaped more by human desire than by physical reality. So we end with something quiet. We end with a recognition that the universe does not owe us intuitive answers. It owes us something rarer. It owes us the chance to learn what is true, even when what is true is not shaped like a human story. The Big Bang is not a myth of creation. It is the earliest chapter our evidence can currently read aloud. And beyond that, there is a silence we have not yet learned how to translate. Not because the universe is empty, but because our knowledge, right now, has an edge. And what waits on the far side of that edge is not a story we can responsibly tell, only a question we can responsibly carry. And maybe that is the final lesson of cosmology. Not knowing is not a failure. It is an honest boundary, a line drawn by evidence, a quiet reminder that the universe is not obligated to fit inside our words, only inside our best, most careful truths.